Today, we're going to get into the science behind why sound can be so weirdly inconsistent, especially in a room. We're talking about a fascinating and sometimes frustrating audio phenomenon known as comb filtering.
You've totally experienced this, right? You're at a concert or maybe just listening to music at home and you find that one perfect spot where everything sounds amazing. But then you move, maybe just a foot to the left, and suddenly, it all falls apart.
Yeah, that's the feeling. In one spot, the bass is punchy, everything's clear, but you shift your weight and boom, it's like the life just got sucked right out of the sound. It suddenly sounds hollow, weak, and just plain wrong.
Well, that strange invisible effect actually has a name. The audio villain behind those sonic dead spots is called comb filtering. So what exactly is it? At its heart, comb filtering is all about interference. It's what happens when a sound, any sound, gets mixed with a tiny, slightly delayed copy of itself. That's the whole secret right there. A sound and its own little echo showing up at the same place at almost the exact same time.
And the name, comb filtering, it's actually super literal. If you were to map out the sound on a frequency graph, the result is this series of sharp peaks and deep valleys that looks just like the teeth of a hair comb. It's a perfect visual for what's happening.
Okay, so we know what it is, but how does it happen in the real world? Turns out the cause is surprisingly simple.
Think about it like this. A speaker makes a sound. Part of that sound wave travels in a straight line directly to your ear. Easy enough. But another part of that same sound wave bounces off the floor or a wall or a ceiling. That reflected path is a little bit longer, right? So it arrives at your ear just a fraction of a second later than the direct sound. When those two signals, the direct one and the delayed reflected one, finally combine, that's when you get comb filtering.
And this isn't just about reflections in a room. You run into this all the time in audio. It happens when you have two mics on one guitar amp and one is just an inch further away than the other. Or when you have two speakers playing the same audio. Heck, some digital effects, like the classic flanger you hear on guitars, are actually designed to create comb filtering on purpose to get that cool swooshing sound.
So, what's really going on when these two signals meet? It's all about physics, specifically phase. At certain frequencies, the waves line up perfectly, they boost each other, and they get louder. That's called constructive interference. But at other frequencies, they're perfectly out of sync. One wave is going up, while the other is going down, and they literally cancel each other out. That's destructive interference, and that's where the real problems begin.
This whole process of boosting and canceling leaves a very distinct fingerprint on the sound. Let's dig into the effects.
And here's where we see that comb again. The constructive interference, where things get louder, creates the peaks. Those are the teeth of the comb. But the destructive interference, the canceling out, creates those really deep valleys in between. In the audio world, we call those deep cancellations nulls.
And what's really wild is that the sound of this effect changes completely depending on how long that little delay is. A really short delay, maybe from a reflection off a nearby desk, creates a comb with wide-spaced teeth, which mostly messes with the high frequencies. But a longer delay creates a much denser comb with tons of tiny teeth, and that can affect the sound all the way down into the bass.
Okay, let's nail down some of the key terms here, because it really helps to separate what you'd see on a computer screen versus what you'd actually hear walking around a room.
So a null is a very specific frequency that gets wiped out. It's that point of maximum cancellation where the direct sound and the reflected sound are perfectly 180 degrees out of phase. That one specific tone can get almost completely erased.
And this is what we actually hear. When those nulls start carving out important frequencies from a voice or an instrument, you get that classic hollow, thin, sometimes kind of nasally sound. All the richness is just gone because parts of the sound have literally vanished.
Now let's take that same idea and apply it to a three-dimensional space. In a room, all this interference creates a physical pattern of loud and quiet zones. We call these lobes. The hot spots are where the sound is being reinforced, and the dead spots are, you guessed it, where it's being canceled out.
So here's the key difference to remember. Comb filtering is the pattern of peaks and nulls you see on a frequency graph. It's a measurement. Lobing is the physical result of that in a room. It's the pattern of loud and quiet zones you can actually walk through. They're really just two sides of the very same coin.
And this quote just nails it, doesn't it? The tonal balance varies dramatically as you move. Even just tilting your head can change the path lengths, which shuffles the entire pattern of nulls and peaks.
The sound is always changing, and it's exactly why no two seats at a concert ever sound quite the same.
So, this is way more than just a neat physics trick. Understanding comb filtering is absolutely essential for anyone who works with sound. Let's talk about why this matters so much. You know, for audio pros, fighting unwanted comb filtering is a huge part of the job. In live sound, the whole goal is to get smooth, even coverage so every single person gets a good show. In the recording studio, it's all about getting clean, full recordings without that thin, hollow vibe from reflections. This is precisely why studios have those foam panels on the walls, to absorb reflections. And it's why big concert speaker systems are designed with such mind-boggling precision. They are actively managing interference to give you the best sound possible.
So the next time you're somewhere and the sound just feels a little off, or you walk right through a dead spot, you'll know exactly what's going on. It's the physics of sound waves messing with each other. So the real question is, now that you know how to listen for it, where are you going to hear it next?